Hi everyone, I'm Mr. Fullerton, and today I'd like to take a little bit of time and talk about relative motion. And we'll do it fairly quickly, in 15 minutes or less, because you've got things to do and physics isn't really that hard. What we're trying to describe here, what we're trying to do is understand what is meant by motion is relative, and we also want to be able to calculate the velocity of an object relative to a reference frame. Reference frame being something that you're observing motion from. So, to define it, a reference frame describes the motion of an observer. The most common reference frame is Earth. Right here, as I'm sitting at my desk, if somebody were to walk in front of me, it would look to me like they are in motion relative to what I see as the room, which is sitting here on Earth. So it looks to me like they're in motion. However, if there was an alien in a spaceship sitting out in outer space with this magic telescope that could peer through the walls of the building, that alien would see that person walking through my room, but they would also see the Earth spinning on its axis. They would see the Earth in orbit around the sun. They would see the sun in our solar system in orbit through our galaxy, and so on and so on. So from that alien's reference frame, it would see much more motion than I'm seeing. That's what's meant by motion is relative. The laws of physics we study in this course are going to assume that we're in a non-inertial, non-accelerating reference frame, which isn't exactly true because typically we're worried about problems here on Earth, and the Earth is spinning on its axis, so we are accelerating a little bit. But typically that is so small that we can make the assumption that we are in a non-accelerating reference frame and everything works out close enough. Finally, there's no way to distinguish between motion at rest and motion at constant velocity in an inertial reference frame. Imagine you're in an airplane, a very, very smooth airplane, and all the window shades are pulled down. You can't tell by any experiment you're going to run in that airplane without putting something outside the airplane, whether you're sitting on the runway, still very smooth, or you're flying through the air at 400 miles per hour smoothly. You could even do something like try and toss a ball up and down. But even in the airplane moving at 400 miles per hour, if you toss it straight up and down, it's going to look to you like it came straight up and down. Now, if the windows were open, a little birdie watching you fly by in the airplane would actually see the ball follow a parabolic path. But from your reference frame, inside the airplane with all the windows down, you can't tell. That's what's meant by motion is relative. So, let's assume that you're sitting in a lawn chair, for some reason, watching a train go by. And on that train, on a table, there's a cup of water. To your reference frame, sitting in the lawn chair, it looks to you like that cup of water is traveling at 50 meters per second. If you were on the train, however, sitting at that table, it would look to you like that glass of water is remaining stationary. On the other hand, imagine you're on the train staring on that poor guy sitting out on the lawn chair watching the train go by. From your perspective, that cup of water is stationary, but that person on the lawn chair is traveling 50 meters per second in the opposite direction, to the left. So really, it depends on your frame of reference. That's what's meant by motion is relative. Now, in order to do some math around these, what we're going to do is we're always going to consider the objects and the reference frames we're dealing with. For example, if we have two objects A and B, say the train and the Earth, calculating the velocity of the train with respect to the Earth is pretty straightforward. You've been doing that for a while. Take the displacement of the train divided by the time it took. There you get your velocity. Speed of a car with respect to the ground, straightforward. If you're walking on a train, the speed of the person with respect to the train, really easy. But what happens when we start bringing in a third object or a different reference frame? For example, we have objects A, B, and C. What we're writing here, the notation says that the velocity of object A with respect to C, our reference frame, is equal to the velocity of A with respect to some object B, an intermediate reference frame, plus the velocity of object B with respect to C. Notice if we want the velocity of A with respect to C, the first letter here is our first letter here. Our last letter is our last letter here. So we bookend the addition of velocities with the velocities that we want. And in the middle, your intermediate letters always have to match. So say we had, let's go with 4 objects, A, B, C, and D. The velocity of A with respect to D would be the velocity of A with respect to B, plus the velocity of B with respect to C, plus the velocity of C with respect to D. That works too, because once again we've bookended our initial and final objects, and in the middle we always have matching B's beside each other and C's beside each other. And that'll work for any number of objects. That's how you can add velocities relatively. Makes a little more sense when you put it into practice. So let's try some examples. If we have a train traveling at 60 meters to the east with respect to the ground, well, let's call to the east our positive direction. So the velocity of the train with respect to the ground is 60 meters per second. And a man on the train runs at 5 meters per second to the west with respect to the train. So the velocity of a man with respect to the train is, since that's to the west, let's make it negative 5 meters per second. Find the velocity of the man with respect to the ground. That must be the velocity of the man with respect to the train plus the velocity of the train with respect to the ground. We've bookended our velocity additions, and in the middle, our intermediates match up. So the velocity of the man with respect to the ground must be negative 5 meters per second plus 60 meters per second, or 55 meters per second. Let's try another one. An airplane flies at 250 meters per second to the east with respect to the air. So the velocity of the plane with respect to the air is 250 meters per second. We'll call east positive again. The air is moving at 15 meters per second with respect to the ground. So the velocity of the air with respect to the ground is 15 meters per second. Find the velocity of the plane with respect to the ground. Well, that must be the velocity of the plane with respect to the air plus the velocity of the air with respect to the ground, which must be 250 meters per second plus 15 meters per second, or 265 meters per second. One last problem and we'll end this video. Two-dimensional problem, relative motion. An airplane flies at 250 meters per second to the east with respect to the air. So the velocity of the plane with respect to the air is a vector 250 meters per second. And the air with respect to the ground is 35 meters per second to the north. Two-dimensional problem, we're setting it up the same way. The velocity of the plane with respect to the ground must be the velocity of the plane with respect to the air plus the velocity of the air with respect to the ground. We've bookended our initial object and final object, and in the middle our letters are the same. This just becomes a vector addition problem then. There's velocity of the plane with respect to the air, 250. Here is our velocity of the air with respect to the ground, 35, both of those in meters per second. So to find the resultant, we take a straight line from the starting point of our first vector to the ending point of the last. And the Pythagorean theorem, when we go through the math, is going to tell us that this is about 252 meters per second. Hope that was helpful. If you need some more practice, why don't you try creating your own relative motion problem involving 3 objects and solve it. And then try one with 4 different objects and see if you can solve it. And of course, if you need more help, you can check out aplusphysics.com. Thanks.